Welcome back, and this week we will continue with our study of forced oscillator, and in this module in particular we will look at resonances, and as usual we will first begin with the quick recap of what we did in the previous module. So, we started by writing down the equation of motion for a forced oscillator, which is this. Once again, to remind you, the forcing or the external forcing really comes from this term here, and omega is the frequency of forcing, and this gamma as usual is the term that represents dissipation in the system, and of course, S is the stiffness coefficient that provides the ingredient for oscillations in the first place. So, together this entire equation in mathematical terms would be called non-homogeneous second order, because it involves d square x by dt square, and it is an ordinary differential equation, meaning that it is not a partial differential equation. And what we know purely as a mathematical problem for class of these kinds of differential equations is that when we try to write out the solution has actually two different parts to it. One is what is called the complementary part, which I have represented by x c here. So, this complementary part would be the solution of the corresponding homogeneous part, which would mean that it would be the solution of, let us call this equation 1, it will be solution of equation 1 with f 0 being equal to 0. So, which is simply the standard damped oscillator that we had already seen, and we already know those solutions. In particular, the solutions there come with the exponential damping factor. And there is a second part of the solution which is called the particular solution, which is denoted by x p here. So, this particular solution is any solution of equation 1 the general solution, which is denoted by x as a function of t here, consists of these two parts, the complementary part and the particular solution. While this is the mathematical sort of description of the solution, we also know that from very physical considerations, complementary part corresponds to damping solutions, which means that they would die away after some time. So, physically they are called transients. So, you would remember that they all come with this e power minus p t multiplied to something. Particular solution would be what is called the steady state. The reason for that is, if I have an oscillating system and it has its own natural frequency of oscillation given by the parameters. Now, if I try to externally oscillate it by giving something like f 0 cos omega t or some other external driving. So, what would happen is that in general the system would adjust its rhythms, so that ultimately after some time it would oscillate at the same frequency with which I am driving the system. So, in that state the transients have died out, what is left is steady state oscillations. So, in the specific case where the forcing is f 0 cos omega t, like the way it is written here, in that case we worked out the solution for displacement and for velocity as a function of time. If you compare with the forcing, which is f 0 cos omega t, you would notice that x of t, displacement as a function of time, comes with a sin omega t. So, clearly there is a pi by 2 difference, phase difference between these two functions, between the forcing and the displacement. In addition, there is also an additional phase difference of phi. So, you can always adjust phi to be 0, but still there would be a phase difference of pi by 2 between the forcing and the displacement. On the other hand, if you look at the velocity as a function of time, so there will be a phase matching between the forcing and the velocity provided phi is equal to 0. If phi is not equal to 0, there will be a phase difference of phi between the forcing and the velocity. So, you can take forcing to be f0 sin omega t, or in general some arbitrary time dependent function which can be resolved in terms of cosines and sines, but ultimately the qualitative results would remain the same. Today we will start by looking at some unusual novel phenomena that would appear when you have both damping and forcing in a oscillatory system. But before we do that, let us take a closer look at this equation. Okay. So, I have the solutions written down here, and if you look at the first one, which is the displacement as a function of time, you will notice that there is a minus I in front of it, and again from the fact that let me write e power I theta, we know that this is equal to cos theta plus I sin theta, and if I need minus I, it will have to be e power minus I pi by 2 will be equal to minus I. So, all you need to do is to substitute theta by minus pi by 2, and you will get this result. So, which means that now I can rewrite this displacement as a function of time by absorbing minus I in the exponential. So, it would be f0 by omega z e power I omega t minus phi minus pi by 2. So, remember that earlier on we had said that between the forcing and displacement there is always a phase difference of pi by 2, even if phi is equal to 0. So, clearly that comes out and it is consistent with that expectation. We would like to look at the phase factor phi as a function of driving frequency omega. To do that, let me once again, and also to remind you, let me write the expression for z. So, we want to look at this, and to do that I need to know what is z, and z is gamma plus I into m omega minus s by omega, and modulus of z is equal to gamma square plus m omega minus s by omega whole square root. So, let us see first what would be the range of phi. So, if omega goes from let us say 0 to, so this is my omega axis, and if it goes from 0 to some really large number, okay, in principle theoretically you can think of it as infinity. In that case, what would be the extremities of phi itself. So, let us say let us put omega here in this equation. If you do that, as omega tends to 0, the dominant term would be minus s by omega. So, it would give me minus infinity. So, tan inverse of minus infinity corresponds to minus pi by 2. So, phi, which will be on the y axis, will run from minus pi by 2 to some large value, which will be determined by the value of omega at the other end. So, as omega tends to infinity, this expression will again be dominated by m omega, because s by omega would tend to 0 as omega goes to infinity, and m omega would tend to infinity. So, tan inverse of infinity would be pi by 2. So, this goes from minus pi by 2 to plus pi by 2, and somewhere in between, when the quantity inside this bracket here is equal to 0, then phi would be equal to 0. So, that would happen somewhere here, and when that happens, phi would be equal to 0 if m omega minus s by omega divided by gamma is equal to 0, and this implies that omega square is equal to s by m, and we know that s by m is what we attribute as the natural frequency of oscillation, and we will denote it by omega square. So, this is the point where omega is equal to, let us say, omega 0, which is equal to square root of s by m. So, we have everything in place, all we need to do is to simply draw the figure, and so now we know that the figure is such that it goes from minus pi by 2 to plus pi by 2. What remains to be done is just to determine how it goes. I will leave it to you as a problem. So, you need to figure out whether from here it goes like this, or it goes like this, or it goes more like this. So, here you just need to find out the slope of phi as a function of omega and find out its value at omega equal to 0. And if you do that, it will turn out that for small values of gamma, it indeed is very close to 0, in which case the expected figure would look something like this. And in principle, one could also draw. So, for instance, if I denote the first curve that I drew by gamma 1 and this by gamma 2, then in this case gamma 2 is larger than gamma 1. And also it is easy to figure out that in this part where the value of phi is negative, velocity leads f in phase. In other words, the phase of velocity leads the phase of the external forcing. On the other hand, in this region phi is positive, it goes from 0 to pi by 2. In that case, velocity lags f, or more precisely the phase of velocity lags that of the forcing term. So, it gives us a global picture of how the phases or the phase difference between velocity and the forcing plays out as you vary parameters. Okay, so, I have the solution for velocity as a function of time here. So, irrespective of what initial conditions we might choose and so on and so forth, the amplitude of the velocity would still be given by this quantity f0 by mod z. F0 is a constant, you really cannot change it because it is a given as part of the problem. You can't change the value of f0 in the middle of the problem. But what you can actually change is this quantity mod z impedance, which depends on the driving frequency omega. So, you can actually tune the driving frequency. So, in that case the question would be, how does the amplitude of velocity, the maximum of that behave as a function of the driving frequency. So, if this is my V max, how does V max change as a function of driving frequency omega? So, that is the question, and it is very easy to see from the expression for mod z that the maximum value of amplitude will come when the denominator is minimum. In other words, the maxima of f0 by mod z will happen when mod z is minimum, and mod z itself will be minimum when, of course, when both this gamma and these two terms are equal to 0, but then we know that we have assumed that there will be a dissipation. So, gamma is not equal to 0, in which case mod z will be minimum when this quantity m omega minus s by omega is equal to 0. So, let us rewrite it slightly differently. So, V max as a function of omega is f 0 by mod z, which will be equal to f 0 divided by square root of gamma square plus m omega minus s by omega whole square. And this, by a small rearrangement, I can rewrite it as f 0 divided by gamma square plus take m square by omega square out, in which case you will get omega square minus s by m whole square. And if you remember, s by m is our omega 0 square, or what we call the natural frequency of the system in the absence of dissipation, in the absence of forcing. Then I will just change the notation, in which case this expression would become f 0 by square root of gamma square plus m square by omega square into omega square minus omega 0 square. So, this is V max and it is a function of omega. So, now we have this in nice functional form, we can now sketch this. So, clearly the maxima of this quantity will happen when omega is equal to omega 0. So, let us sketch that. So, I am plotting V max as a function of omega, and from the expression that I have here, it is very clear that when let me call this point omega equal to omega 0. So, that would be the point at which the maxima of V max will occur, and for any other value of driving it is going to decrease, and forgotten a 2 here. So, it is going to decrease quadratically. So, the functional form would look something like this. So, a curve of this type is called the resonance curve. So, it tells me the following important physical information. So, I have a damped forced oscillator, I keep driving the system, and let us say that I am varying the angular frequency of the external drive. So, at some point when the frequency of the external drive is equal to the natural frequency of the system, the response of the system is going to be large. It is going to be responding the greatest when the external driving frequency matches the natural frequency of the system. For any other value of drive frequency, the response is going to be really small, and it is going to drop off quadratically. So, this is what would be a resonance curve for velocity. One could ask similar question of displacement as well. So, we can think of displacement resonance. So, this is velocity resonance. So, physically when we say that velocity resonance is happening, it means that the velocity of the oscillating particle is going to be a maxima. Okay. So, before we look at the displacement resonance, let us, as we did for the case of velocity, let us first look at how phi changes with the angular frequency. So, phi is the phase difference, and of course, I have the standard driving term here given by f 0 e power I omega t, and I have the displacement as a function of time. So, here I have absorbed this minus I which is here in the exponential, and so it shows up as a phase factor. Remember that in one of the earlier modules we said that when you multiply by I, it is equivalent to turning the vector by pi by 2. So, when you multiply by minus I, it is equivalent to adding this phase of minus pi by 2, and of course, modulus Z is what we already have all along. So, now the total phase angle would be the following. So, as usual you subtract this I omega t and I omega t, that goes away. So, the total phase angle is minus phi minus pi by 2, whereas just the phase angle alone would be simply phi itself. So, now let us, since we want to plot phi versus the angular frequency omega, let us first look at the range of these quantities. Let us sketch the total phase angle. Let me write it here, total phase angle. I am going to sketch this as a function of omega on x axis, and I can also plot phi, just the phase angle on right hand side. So, if you remember from our previous arguments, phi goes from minus pi by 2 to plus pi by 2, because the expression is still the same whether it is velocity or displacement, phi will still go from minus pi by 2 to plus pi by 2. So, let us say that here it will go from minus pi by 2 to plus pi by 2. On the other hand, when phi is equal to minus pi by 2, the total phase angle would be simply equal to 0. That is because you simply substitute minus pi by 2 here in the value of phi, that will just give you 0, and when phi is equal to plus pi by 2, it will give you minus pi. So, the value here would be equal to minus pi. So, now all we need to do is to simply plot the functional form of this phi equal to tan inverse of m omega minus s by omega divided by gamma. So, here again I leave it as an exercise for you to do it yourself, but the curve should look something like this. And here this is the point where total phase angle is 0. Right. So, imagine if total phase angle is 0, this quantity here is 0, which means that displacement and forcing are in phase. So, that is the point where displacement and forcing are in phase. The phase difference between them is 0, and this would be a point where x would lag in phase with respect to that of f, and again here x lags f. So, with a little bit of thought you can figure out these differences in phase between displacement and forcing. And here I am not going to draw the case for two different values of gamma. Again I leave it to you as an exercise to draw similar function for two different values of gamma, where one is greater than the other. Now, with this let us go to the question of displacement resonance. So, the question there is identical to what we asked when we looked at velocity resonance. So, I have the solution for displacement as a function of time, and you will notice that maximum amplitude would simply be f 0 by omega mod z. Let us write that x max would be f 0 by omega mod z. So, here again the question is same. If I were tuning omega, if I were changing the frequency of driving, how would x max change? So, remember that unlike in the previous case, here the question is slightly little more complicated, because you have a omega here, but there is also omega inside this modulus of z. So, we need to minimize this function with respect to omega. As usual, the argument is that x max would be maximum when the denominator is minimum. The denominator here is omega modulus z. So, since we want to find the minimum of the denominator here, what we need to do is to differentiate the denominator with respect to omega, set it equal to 0 and find the value of omega. So, we can do this as a as part of one of the problems, but if you do it, which is straightforward to do, the result that you will get is that omega square is equal to omega 0 square minus gamma square by 2 m square, where omega 0 square is s by m, which is called the natural frequency of the system, without either damping or the forcing. So, with this ingredient, we are sort of ready to sketch the displacement resonance curve. So, here you notice that the resonance or the maximum value of x max happens at not at omega 0 square, but at a value of frequency that is slightly below omega 0 square. So, you could see that it is omega 0 square minus gamma square by 2 m square. So, what we are going to get is a series of curves that would look like this. Let me sketch them for you now. I have sketched the displacement resonance curve. So, you will notice some important features. One is the maxima takes place, maxima of displacement happens at a value of omega which is less than omega 0, and it changes with gamma as well. As you increase dissipation, the maximum value of course decreases, which is what you would expect naturally from just the physical intuition. Just to interpret this curve physically, it tells us that if you have an oscillating system which is both damped and you are driving it with some angular frequency, and if you are changing the angular frequency, then the response of the system would be greatest. The response here is measured in terms of the amplitude of the oscillation. The amplitude of the oscillation would be largest at a value of driving frequency which is slightly lesser than the natural frequency of the system. So, this would be called displacement resonance or simply resonance. To summarize this module, what we saw is we looked at both the solutions that we obtained for the driven damped oscillator, both the solutions, meaning that we looked at the displacement as a function of time and velocity as a function of time, and we tried to closely see what happens if I tune the angular frequency with which I am driving the system. So, you look at the phase difference between velocity and the forcing as a function of omega, and that is what is sketched here in front of you. So, there is a range of frequency values below omega 0, which is the natural frequency, where velocity leads f in terms of phase, and if driving frequency is larger than the natural frequency, v velocity lags driving frequency in phase, and that is as far as velocity is concerned. And we also looked at the idea of velocity resonance. So, you ask what is the maximum amplitude of velocity, how does it change with driving frequency. Interestingly, it turns out that when the natural frequency is equal to the driving frequency, velocity is, the amplitude of velocity is maximum. And exactly identical questions can be asked about displacement as a function of time. So, we did that. So, we looked at how the phase angle varies as a function of omega. So, again that is the curve that is sketched in front of you here, and we also looked at the idea of displacement resonance. In the next modules, we will look at how we can quantitatively describe these resonances. So, we will be coming back to the idea of Q values or Q factor that we saw earlier.